Hello dear students, welcome to this second part of video lecture on the topic that is solids. I am Dr. Smita Pimple, Professor in Pharmaceutics Department at Modern College of Pharmacy, Nigdi, Pune. So students, we were studying about the solid state. We have seen that it has two major categories, crystalline and amorphous, and before studying in detail we need to understand definitions. We studied about crystal lattice, unit cell, crystal habit, crystal faces, interfacial angle, and we understood the meaning of isotropic and anisotropic properties. Now, important phenomena regarding crystal or crystallinity is polymorphism. Now, polymorphic forms you must have studied previously. Polymorphism is the phenomena of existing same material which is having same molecular formula, but they exhibit different crystalline forms. They are referred as polymorphism or polymorphic forms. They are categorized as metastable, monotropic and enantiotropic. So metastable polymorphic form is the one which is highly unstable and prone to get converted in thermodynamically most stable polymorphic form. Monotropic, when the transition takes place in one direction only. For example, from a metastable to a stable form, the change is said to be monotropic. Enantiotropic, when the change from one polymorphic form to another is reversible, then it is said to be enantiotropic. So, for example, a drug which exhibits polymorphic forms A, B, C. So, suppose B is a metastable form, then B will always try to get converted in more thermodynamically stable form. For example, most stable form might be A. So the transition from B to A, if this transition is in one direction only, then it is said to be monotropic. But if it is reversible from stable form to again converted to another polymorphic form, then it is said to be enantiotropic in nature. Now, crystallization process. So the basic crystallization process we can study under three subheadings, that is supersaturation, nucleation or nuclear formation and crystal growth. So first you need to supersaturate the solution with the entity which you want to crystallize. So if you want to crystallize certain salt, just dissolved in water, and you need to have concentration beyond saturation level. Everyone knows that what is saturation? It is the maximum capacity of solvent is being used to solubilize the solute. But how you could achieve supersaturation? Now, most of the solids, they follow this rule. We can say that as the temperature increases, the solubility of the solute also increases. This is true when the process of solubilization of the solute is endothermic. Okay, when the process of solution is endothermic, then when temperature is increased, the solubility is going to increase. Now, in such cases, you can achieve supersaturation by dissolving a high amount in the solvent. Increase the temperature. Because of increase in temperature, you will get more amount of solute dissolved in the solution. And if you later decrease temperature, then the all dissolved solute is not coming out of the solution. Okay, so this is referred as a supersaturation or supersaturated solution. That means holding solute molecules beyond the solubilizing capacity of solvent. And once you achieve this, and if this is subjected to freezing or like decreasing the temperature with continuous stirring, then the crystallization process will start. First, there will be formation of nuclei. That means very small lattices or crystals, they are separating from the solution. Here you can see that initially you have a supersaturation achieved in a solution, and as you decrease temperature with stirring, there is formation of very small crystals, or they are referred as nuclei, very few lattices joining together to develop this nuclei. And then later on, the next further step with time, there is deposition of more molecules or the particles, and the lattice grows in size, or this nuclei, they grow in size to give a formal final crystal shape. So this is the usual crystallization process where you need to achieve supersaturation. The nucleation will start with decrease in temperature, and with a certain time period subjected to stirring and cooling, you will be getting this nuclei developed into the final crystals. So this is about crystallization process, and it depends upon the level of supersaturation, the rate of cooling, rate of stirring. These will be affecting the homogeneity and the size of the crystals. Now next is we are going to study about Brevis Lattices. So Brevis, he is a scientist who has categorized or who has classified the different crystal lattice structures depending on certain parameters. Now students, to understand this, we are going to study very simple lattice structure, that is cube. You all know that the cube has all sides equal, okay, and the interfacial angle in the cube, it is 90 degrees Celsius. Means, for example, in this shape you can see the sides given name A, B, C. For example, these three sides, okay, along the three axes like x, y and z axis, along these three axes, consider these three lengths A, B and C. So if all the lengths are same, if A is equal to B and B is equal to C, all three lengths are same, and if interfacial angle between the faces, for example, this is referring to a single face. A cube has 6 faces, okay, one is top, one is bottom, and 4 along 4 directions. So these 6 crystal faces are there in the cubic shape. So the angle between any two adjacent faces is nothing but the interfacial angle, and along the three axes, if we consider, we have given the name alpha, beta and gamma. So if three lengths are same and if three interfacial angles are same, that is 90 degree, then you are bound to get the lattice structure as a perfect cube. Okay, now this is the basic crystal lattice shape. Now the variation in this shape, depending on the arrangement of the molecules or the particles you can get, is it is referred as P when you are getting the particles at the corners of the cube. Okay, if you have a molecule placed exactly in the cavity of the cube at the center of this cube, then it is referred as I. And if you are getting a particle placed at the center of each face of the cube, then it is referred as F. The meaning of this is the P is primitive, that is there is only one reticular point inside the lattice cell. C is centered in the faces, perpendicular to the cell C axis. This we are going to see later. But what is I? We have seen I is centered in the body of the cell. And F, it is referred as the centered in all faces of the lattice cell. And R will be referred to primitive, identical cell axis and cell angles, or hexagonal, 2 times body centered. Now we are going to see this in further structures. Now, like this is a tetragonal structure. Okay, what variation we have with respect to cubic in tetragonal lattice shape is two sides are equal but one is not equal. That means A is equal to B but it is not equal to C. And all three interfacial angles, they are same, that is 90 degree. So primitive, that means only the particles are located at the corners of the tetragon. Then I refers to centered in the body of the cell. You can see here one particle is placed in the center. And trigonal or hexagonal, this lattice shape you will get when A is equal to B, B is not equal to C, when alpha and beta interfacial angles are equal to 90 degree, but when the third interfacial angle, gamma, when it is equal to 120, then you are going to get a trigonal or hexagonal primitive lattice shape. Now this trigonal R, where you can see, okay, the particles are placed such that you can imagine in this manner also, like a cube is entrapped inside a trigonal or hexagonal shape. So that is referred as a R. So different Brevis lattices are there, like triclinic, where A is not equal to B, B is not equal to C, but the alpha, beta and gamma, they are also not equal to 90 degree exactly. There are changes, so you are getting triclinic, monoclinic, it can be primitive. In monoclinic, A not equal to B, B not equal to C, beta is not equal to 90 degree, but alpha and gamma 90 degrees. So you are getting a monoclinic type of lattice shape. So likewise, Brevis has differentiated the different lattice shapes based on the length ABC and the interfacial angle. So these are orthorhombic, they can be primitive, or like you can see here, different types of structures are possible. Now this is about lattice structures. Now depending on the crystal habit, okay, that means the lattice is joined to give the crystal a external shape which is referred as habit. It may develop into different shapes, so they can be pyramidal. So different crystal habits and their diagrammatic representation is there in this figure. You can see pyramidal habit, twinned, or cube which is having 6 faces, or acicular, that means needles. There can be tetrahedron, equant, pyrethrohedron, or radial type of habit, or scalenohedral, fibrous, prismatic, cylindrical, tabular, dipyramidal. Okay, so different kinds of crystal habits are possible based on how the lattices are joined together. So students, this is all about the basic crystal lattice and habits. Now in next lecture we are going to study about polymorphism and the significance of polymorphism in the pharmacy.